Cambridge Primary Science. 5 electrical conductors and insulators. 5.1 Which materials conduct electricity? In stage 4, you learnt about electric current. An electric current needs a continuous path. This path is called an electric circuit. So far you have used the word cells for the energy storage units like the ones in a torch. Each cell stores 1.5 volts of electricity. When we have 2 or more of these cells connected together, we call it a battery. Cells and batteries push electricity round a circuit. What are conductors and insulators? Words to learn. Battery. Conductor, insulator. The metal wire is made of copper and it carries the electricity. Materials like metals allow electricity to pass through them. A material that allows electricity to pass through it is called a conductor. The copper wire is covered with plastic. This material does not allow electricity to pass through it. It is called an insulator. Activity 5.1. Test materials to see if they conduct electricity. You will need 3 wires, sticky tape, a screwdriver, a 1.5 volt cell, a 1.5 volts bulb in a bulb holder, objects made of different materials. Attach wires to the cell and bulb holder. Connect the third wire to the bulb holder and leave the other end free. Check that your circuit works. Hold the bare ends of the wires together. If the bulb lights up, the circuit works. Separate the ends and the bulb goes out. This is your testing equipment. You will use this to see which materials allow electricity to pass through. Before you begin, predict which materials will allow electricity to pass through and which will not. Record your predictions in a table. If the bulb does not light up, then you can try again. To make sure, record your results in the last column of your table. Questions. Test each material. Hold the bare end of one wire at one end of the object. Hold the second bare wire at the other end. 1. How well did your results support your predictions? Safety. Do not touch any bare electric wires. Always hold the plastic-covered wire. 2. Identify which types of material are conductors and which are insulators. 3. Did any materials not fit this pattern? If so, identify the material. 4. What conclusion can you make from your results? What you have learned: metals conduct electricity and are called conductors. Other materials do not conduct electricity and are called insulators. Talk about it. What would happen if the wires in a circuit were not covered in plastic? 5.2 Does water conduct electricity? Is water pure? Water from a river or the tap is not pure. It has salts dissolved in it. Pure water is distilled water. This is water that has been boiled and the steam has been condensed. The condensed steam does not contain any dissolved salts. You are going to investigate whether pure water and salty water conduct electricity. Words to learn: pure, distilled. All living things contain water. Our bodies are about 65% water. This water has substances, including salts, dissolved in it, so it is not pure. Oh, it is. Activity 5.2. Investigating whether water conducts electricity. You will need a circuit with 3 volts battery as shown in the picture, distilled water. 2 teaspoons of salt, aluminium foil. Connect up the circuit with the battery, the bulb in the bulb holder and 3 lengths of wire. Fold the pieces of aluminium foil and press them to the bare ends of the wire. Pour 250 milliliters of distilled water into the beaker. Dip the aluminium foil ends into the water. Predict whether the bulb will light up. 0002 IPI 9 meters Tren. Test the circuit by holding the bare ends of the wires together. Does the bulb light up? Add 2 teaspoons of salt to the water and stir it. Now dip the aluminium foil ends into the salt water. Predict whether the bulb will light up. Observe whether the bulb lights up. Questions. 1. Did your results support your predictions? 2. Compare the result you got with pure water and with salty water. 3. What conclusion can you make about whether water conducts electricity? 4. Would you be a good or a bad conductor of electricity? Explain why. 5. Look at the picture of Lan in the bathroom. What is she doing that is dangerous? Explain why it is dangerous. What you have learnt. Pure water does not conduct electricity. Water with salts dissolved in it does conduct electricity. Talk about it. How do you know that the water in our bodies is salty? 5.3. Do different metals conduct electricity equally well? Measuring current. Current is the rate at which the electric charges flow. You will measure current in activity 5.3. We measure current by the number of charges that flow through a point in a circuit in 1 second. We measure current in units called amperes or amps for short. We use an instrument called a multimeter to measure current. The multimeter has connectors. Metals and alloys. Many objects are made of a combination of different metals. These are called alloys. Stainless steel is a mixture of iron, nickel and chromium. Brass is a mixture of copper and tin. Activity 5.3. Investigating how well metals conduct electricity. Words to learn: ampere multimeter. Connectors. 000. A multimeter. You will need plastic covered wire, sticky tape, a screwdriver, a 1.5 volt cell, a multimeter, some metal objects. Safety. Do not touch any bare electric wires. Set up your circuit like this. Connect the positive end of the multimeter to the positive terminal of the battery. Check that it works. Hold the plastic coated wire and let the bare end touch the connector of the multimeter. A reading on the multimeter shows that the circuit works. This is your testing equipment to see how well metals conduct electricity. Before you begin, predict which metals will be the best conductors. Record your predictions in a table. If the multimeter doesn't show a reading first time, then check again. Record your results in a table. Test each metal. Hold the bare end of one wire to one end of the object. Hold the connector of the multimeter to the other end of the object. Read the current in amps on the multimeter. Questions. 1. Did all the metals conduct electricity? 2. Which metal was the best conductor? How did you know this was the best conductor? 3. How well did your results support your predictions? 4. What conclusion can you make from your results? Challenge: gold is a very good conductor of electricity. Why isn't gold wire used in circuits? What you have learnt. All metals conduct electricity, but some metals conduct electricity better than others. Talk about it. Why are lightning conductors made from copper? 5.4. Choosing the right materials for electrical appliances. Conductors, insulators and mains electricity. Word to learn: plug. In stage 4, you learnt about mains electricity, which has a voltage of 110 volts in some countries and 220 volts in others. At these high voltages, safety is very important. The parts of an appliance that you touch must be made from an insulating material. The parts inside the appliance are made from conducting material so that electricity can pass through. You saw in activity 5.3 that metals are good electrical conductors. The parts of electrical appliances that let electricity pass through are made of metal. For example, metal is used for the metal pins in a plug. The pins allow electricity to travel from the wall socket, through the plug, and into an appliance such as a kettle or television. When we handle the plug, we only touch the cover. This is made of plastic, which is a good insulator. Look at the diagrams. Discuss the use of conductors and insulators in these components. A switch. A switch cover. Made one like this in stage 4. Plate for mains electricity. Using mains electricity safely. If mains electricity flows through your body, then you will get an electric shock. You will be badly burnt, your heart could stop and you could die. Damaged electrical wiring is a major cause of accidents with electricity. Plastic insulation often wears off the copper wires. You can get a shock if you touch the wires. A piece of electrical wire. Here are 2 ways that electrical wires get damaged. Wires. Never place an electric wire under a carpet. When people walk on the carpet, the plastic wears off the copper. When copper wires touch each other, electricity flows between them and this can start a fire. Never pull a plug out like this. This damages the cord and the wires become bare. Grip the plug to pull it out of the socket. Turn off the switch before you pull out the plug. Questions. 1. Find appliances at home or at school that use conductors and insulators. A. List the appliances. B. Choose one example. Draw it and label the materials used. Say whether they are conductors or insulators. 2. Predict what could happen to the people in picture A and picture B. B. Explain why this could happen. 3. Make a safety poster warning people about the dangers of electricity. What you have learnt. A. 0. B. Electrical appliances are made up of materials that conduct electricity and insulating materials that do not conduct electricity. Knowing about electrical conductors and insulators helps us to use electricity safely. Talk about it. Talk about electrical conductors and insulators in your classroom. 5.5 Circuit symbols. So far we have shown circuits using pictures like the one on the left. This is a series circuit, which means there is only one path for the flow of electricity. Describe what is in this circuit. Words to learn. Series circuit. Circuit diagram. The picture on the right is a circuit diagram of the same circuit. We use symbols to draw circuit diagrams. This is much quicker than drawing pictures. People all over the world can understand circuit diagrams because everyone uses the same symbols. Here is a list of circuit components and their symbols. 1.5 V cell. 2 1.5 volt cells joined together. 3 V. 3 volts battery. The open switch, closed switch, bell, connecting wire, bulb, buzzer, motor. M. Questions. 1. Look at circuit diagrams A, B and C. Identify the circuit that shows I. A battery, a buzzer. Circuit A, circuit B, and a switch. Circuit C. E. A cell, a bulb and a switch. E. A cell and 2 bulbs. B. Which circuit shows the switch open? C. Which circuit has the biggest energy source? How do you know? 2. Draw a circuit diagram to represent the circuit on the right. 3. Draw a circuit diagram to show a circuit with a 3 volts battery, 2 bulbs and a closed switch. What you have learnt. Circuit symbols represent the components of an electric circuit. A circuit diagram shows where components are found in the circuit. Talk about it. What other symbols do we use every day when we communicate? 5.6 Changing the number of components. Some circuits have lots of components. Activity 5.6 Making a circuit with more components. Make the circuit using one of the bulbs as shown in this diagram. Close the switch. Observe the bulb. Open the switch. Predict what would happen if you add one more bulb in a bulb holder to the circuit. Test your prediction. Did the bulbs shine more brightly or less brightly when you added a second bulb? Why? Activity 5.6b. You will need a 1.5 volt cell, 2 bulbs in bulb holders, a switch, 150 centimeters wire, a sharp knife, scissors, sticky tape. Discussing and planning your own investigation. Here are 2 questions for you to test. If you remove a bulb from a circuit with 2 1.5 volt cells joined to make a 3 volts battery and 3 bulbs, will the bulbs glow more brightly or less brightly? 2. If you add a third 1.5 volt cell to the same circuit you used in 1, will the 2 bulbs glow more brightly or less brightly? Discuss how. You will plan an investigation to answer these two questions. Choose what components you need to make your circuit. Use your knowledge of electrical circuits to predict what will happen when you carry out the tests. Make your circuit. Observe what happens when you remove the bulb and then when you add another cell. Does the evidence support the predictions you made? Repeat any observations that you are not sure of. Use your results to answer the questions that you were asked to test. Questions. 1. Draw a circuit diagram for each of the circuits you made in Activity 5.6b. 2. Look at Circuit A and Circuit B. Predict in which circuit the bulbs will be brighter. Circuit A. Circuit B. Ho. 3. Suggest another circuit question that you investigate. Could what you have learnt. Removing or adding bulbs from a circuit causes them to glow more or less brightly. Adding or removing cells used in a circuit causes bulbs to glow more or less brightly. Talk about it. If a circuit doesn't work, what must you check? 5.7 Adding different components. Alfonso, why won't my car go? You haven't got enough batteries in it, Pedro. Let me fix it for you. Different components need different strengths of electricity. You can put buzzers, bells and motors in a circuit instead of a bulb. These components need a stronger supply of electricity than a bulb. Voltages. The strength of electricity is measured in a unit called a volt. V. Dot. The strength of electricity that a component needs for it to work is called the voltage. Look at the voltage of these components. This bell needs 6 volts to work. This bulb needs 1.5 volts to work. This buzzer needs 3 volts to work. This motor needs 24 volts to work. If you put a 3 volts buzzer into a circuit, you need a 3 volts battery to make the buzzer work. You can make a 3 volts supply by joining two 1.5 volt cells. Activity 5.7. Building circuits using different components. Plan and build a circuit with a battery, a switch and a buzzer. You will need 2 batteries, a switch, a buzzer connecting wires, a motor, black circle, a bell. Test whether adding another battery will make the buzzer sound louder. Decide how you will change the circuit if you replace the buzzer with a motor or a bell. Discuss how you will make the circuits. Choose what components you need. Predict what will happen before you make each circuit. Make your first circuit. Does the buzzer work? Add another cell to the battery. Observe any differences. Make the changes you plan to replace the buzzer with a motor or a bell. Predict what will happen. Does the evidence support the predictions you made? Repeat any observations that you are not sure of. Questions. 1. Draw a circuit diagram for each of the circuits you made in Activity 5.7. 2. Think about when you added an extra cell to the battery in your buzzer circuit. What was your conclusion about the effect of this? 3. Look at circuits A, B and C. The bell and buzzer need 6 volts to work and the motor needs only 1.5 V. A. Predict which of these circuits will work. B. Explain why the other circuit does not work. What you have learnt. Different components need different strengths of electricity to work. Changing the number of cells affects how well components work. Ho. Circuit A. Circuit C. Circuit B. Talk about it. What do you think a 1.5 volts and a 12 volts motor could be used for? 5.8 Length and thickness of wire in a circuit. Look at the children watering the garden. The pressure of water coming from the taps is the same for each of the 4 hose pipes. The hose pipes supply different amounts of resistance to the water passing through them. If there is a lot of resistance in the hose pipe, less water comes out than if there is not much resistance in the hose pipe. Sam has a long hose pipe and Pamela has a short hose pipe. Their hose pipes are the same thickness. Look at the long hose pipe and the short one. Which has the most water coming out? Which hose pipe offers the most resistance to the water, the long one or the short one? Words to learn. Pressure. Resistance. Vuzi. Mary. Sam. Vuzi has a thin hosepipe and Mary has a fat hosepipe. Their hosepipes are the same length. Which has the most water coming out? Which offers the most resistance to the water, the thin one or the fat one? You can apply what you know about water flow in hosepipes to electric current flow in wires. Activity 5.8. Changing the thickness of wire in a circuit. Set up a circuit as shown in the diagram. Insert 10 centimeters of thin resistance wire into the circuit. Measure the current on the multimeter. You will need two 1.5 volt cells wire, thick and thin resistance wire, a multimeter crocodile clips. Now replace the thin resistance wire with the same length of thick resistance wire. But before you do this, predict whether the multimeter reading will be higher or lower. Test your prediction. Do you think changing the length of resistance wire will change the multimeter reading? Discuss how to test this and how much evidence you will need. Test your prediction. 3.061. Questions. 1. Copy this sentence, choosing the correct word where there is a choice. Long or thin hosepipes give more, less resistance to water flow than short or fat hosepipes. B. Write a similar sentence about the flow of electricity through different wires. 2. How did changing the resistance wire from thin to 3 thick change the multimeter reading? B. Explain why this happened. How did changing the length of resistance wire change the multimeter reading? B. Explain why this happened. What you have learned. Changing the length or thickness of wire in a circuit will change the strength of current. Challenge. Extension cables are often 30 meters long. Why are these cables made of thick wire rather than thin wire? An extension cable. Talk about it. How has thin wire been put to good use in a light bulb? 5.9. How scientists invented batteries. All the circuits you have made have included a cell or a battery. These batteries contain chemical substances that react together. This reaction supplies the energy needed to push the electricity round the circuit. How did scientists make this discovery? The Baghdad battery. In June 1936, workers found an ancient tomb while they were constructing a new railway near the city of Baghdad, in present-day Iraq. Archaeologists identified things in the tomb to be 2,000 years old. At this time, people called the Parthians lived in this region. One of the old objects or relics they found in the tomb was a clay jar. The jar had an iron rod coming out of the center, surrounded by a tube made of copper. Scientists made copies of it relic. When they filled the tube with an acid such as vinegar, it produced between 1.5 and 2 volts of electricity between the iron and copper. Archaeologists think that people who lived 2,000 years ago could have used batteries like this to cover metal objects with gold. Galvani's discovery. Luigi Galvani was an Italian doctor. About 1780 he discovered current electricity. He hung a frog's leg on copper hooks over an iron railing and noted that the leg muscles twitched. Galvani was correct when he said that the twitchings were caused by electrical current, but he thought that the current came from the frog's leg nerves and called it animal electricity. Single quote. The voltaic pile. Alessandro Volta was an Italian university professor. He repeated Galvani's experiments many times with different materials. From these experiments he came to the conclusion that it was the two different metals, copper and iron, not the frog's leg, that produced the electricity. The frog's leg contained a fluid which conducted the current. It twitched because the electricity was flowing through it. In 1800, after many experiments, he developed a type of battery that he called the voltaic pile. This consisted of a pile of zinc and copper discs. Between each disc there was a piece of cardboard that he had soaked in salt water. A wire connecting the bottom zinc disc to the top copper disc could produce a continuous flow of sparks. Volta built different piles using 30, 40 or 60 discs. He measured the reaction with different numbers of discs and discovered that the electric shock increased in intensity with the number of discs he used in the pile. Later, scientists improved Volta's battery by doing more experiments. Questions. 1. What did Galvani observe in his experiments with frogs' legs? 2. What did these observations lead Galvani to conclude? 3. How did Volta use creative thinking to develop Galvani's ideas further? 4. What measurements did Volta make to provide evidence for the strength of electric current? 5. Describe the differences between Galvani's and Volta's explanations for how an electric current flowed. 6. What electrical unit is named after Volta? What you have learnt. Scientists have combined evidence from observation and measurement with creative thinking to suggest new ideas and explanations for batteries and electricity. Talk about it. How could people have invented batteries 2,000 years ago? 5. Check your progress. 1. Copy the words in column A and write their correct meanings. From column B. Next to them. Column A. Ampere. Volt. 2. 3. Multimeter. Series circuit. Circuit diagram. Resistance. Connector. Plug. Column B. A picture of a circuit using symbols. A device to connect two wires together. The unit for measuring the strength of electricity. The unit electric current is measured in. A piece of equipment for measuring current, voltage and resistance. A device for connecting an electric wire or cable to an electricity supply. A circuit where the electricity only has one path to flow along. The amount of restriction of flow of electricity. What is the difference between a cell and a battery? B. An electrical conductor and an electrical insulator. C. Pure water and distilled water. Draw a circuit diagram including these components to make the circuit. 4.5 volts battery connecting wire switch. 2 bulbs. 4. A. In which of the circuits A, B and C will the bulb not light up? Explain your answer. H, B, R, C. 5. 6. Explain why plug covers are made of plastic and electrical wire is made of copper. Identify 2 dangers in the use of mains electricity in the picture. Reference. How to plan an investigation. Making an idea into a question. Stirring makes sugar dissolve more quickly. Stirring makes no difference. It just makes the spoon clean. Amna wants to test her idea. She makes it into a question. Does stirring make sugar dissolve more quickly? Single quote dot. Choosing the equipment. We can put sugar in 3 cups of tea and stir. Each cup a different amount. But tea is too dark. And we need a watch to see when the sugar has dissolved. They decide to dissolve the sugar in hot water and use clear containers. They put the containers onto black card. This will help him to see the sugar. Netta gets a stopwatch so that they can measure how long the sugar takes to dissolve. No stirring. Stir 3 times every 2 minutes. Stir 3 times every minute. 0. 0, 0, 0, 0. Making the test fair. What do they need to keep the same to make the test fair? They make a list of the variables. Making the test accurate. Variables. Amount of sugar, amount of water, temperature of water. Amount of stirring. It will be hard to see exactly when all the sugar has dissolved. We can repeat the test to make it more reliable. It is not important who stirs the sugar in this investigation. Choosing equipment. It is important to choose the right science equipment for an investigation. Using the right equipment can make measurements more accurate. Sunil wants to measure how much water he has. He can see it is between 70 and 80 milliliters, but he wants an accurate measurement. Dash, 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 dash. 100, 80, 60, 40, 20, 0. Sunil knows that he needs to use a measuring cylinder, but he is not sure which one. Look at the water in the measuring beaker. Which measuring cylinder will give the most accurate measurement? The 50 milliliters measuring cylinder is too small. 50. 1 milliliter. 100, 2 milliliters, 250, 5 milliliters. This one is best. I can see I have 73 milliliters. Water. 80, 250, 5 milliliters. 70, 250, 50, 200, 60, 150, 100, 50. Sunil tries the others. For an accurate measurement, use the smallest measuring cylinder that the liquid will fit into. Use this page to help you choose what you need for your investigation. 00. Digital timer. Measuring beakers. Scales. Dropper. Thermometer. Measuring spoons. Filter paper. Sieve. Scales. 8888. Rulers. Measuring cylinders. Multimeter. 1.5 volt cell. Motor. Funnel dropper. Bulb in holder. Force meters. Tape measure. Using force meters. Scales using a force meter. Turn the nut to check the force meter is set to 0. Put the object on the force meter. Put your eye level with the pointer and read the scale. The weight of the bananas is a force of 4 newtons. Many force meters also have a scale that will show the mass of an object in grams or kilograms. The bananas have a mass of about 400 grams. Some force meters can also be used to measure the size of a pushing force. A force of about 2.5 N is needed to push this book across the table. Using scales. These scales are not set to 0. Look for a wheel at the back of the scales. Turn the wheel to set the scales to 0. 800, 900, 1 kilogram, 100, 200, 300, 700, 600,500. Down pointing arrow. 900, 1 kilogram, 100, 200, 800, 700, 300, 600,500,400. Put an object on the scales. The scales will show the mass of the object. This apple has a mass of 250 g. 1 kilogram. 900, 100, 200, 800, 300, 700, 600, 400, 500. Looking for patterns in results and making conclusions. There are often patterns in results. The pattern might be results that are all the same, or it might be measurements that go up or down. Femi and Kwasi are investigating which materials conduct electricity. They are testing objects made from different materials. The bulb lights when the material conducts electricity. Here are their results. Object. Material. Bulb. Scissors. Metal. On. Ruler. Wood. Off. Cup. Plastic. Off. Cup. Glass. Off. Key. Metal. On. Coin. Metal. On. Book. Paper. Off. Spoon. Metal. On. Spoon. Wood. Off. Pencil lead. Graphite. On. Pen. Plastic. Off. Femi has seen a pattern in the results. Some of the results are the same. He uses the pattern to make a conclusion. Is Femi correct? Kwasi has seen a result that does not fit the pattern. To check that they have not made a mistake, they repeat the test with the graphite. The bulb lights up every time. So Femi's conclusion is not right. They make new conclusions. Metal conducts electricity. Materials that are not metal do not. Some materials that are not metal do conduct electricity. Using patterns to check that repeated measurements are reliable. Yoko and Marja are investigating how running affects pulse rate. They want to know if their pulse rate is different when they run at different speeds. Yoko runs the same distance each time but at 3 different speeds. To make their results reliable, Yoko runs at each speed 3 times. They measure her pulse rate after each time. They are going to take the average pulse rate for each running speed by finding the mean. Is your pulse rate different if you run at different speeds? Here are their results so far. Exercise. Running very fast. Running quite fast. Running slowly. Pulse rate 1 in beats. 190. 102. 155. Per minute. Pulse rate 2 in beats. 195. 172. 153. Per minute. Pulse rate 3 in beats. 188. 178. 210. Per minute. Mean pulse rate in beats per minute. The girls look for patterns in their results. The numbers for running very fast are almost the same. But there are two measurements in the results that could be wrong. Look for numbers that do not fit the pattern. The girls repeat two measurements to check that they are reliable. Then they calculate the mean. Their results now look like this. Exercise. Running very fast. Running quite fast. Running slowly. Pulse rate 1 in beats. 190. 102,169. 155. Per minute. Pulse rate 2 in beats 195. 172. 153. Per minute. Pulse rate 3 in beats. 188. 178. 210,148. Per minute. Mean pulse rate in 191. 173. 152. Beats per minute. Marja makes a conclusion. The faster you run, the faster your heart beats. When you repeat. The girls explain why they repeated their measurements. Measurements, it is easier to see if you have got one of them wrong. Also, you can find the mean so your results are more reliable. Researching questions. Sometimes a science investigation is not the best way to answer a question. You may not have the equipment you need or enough time. The answers to many questions can be found in reference books or on the internet. Mai is researching food chains. Choosing keywords. First, search. You should think about which words to look for. These should be keywords for the topic you are researching. Mai could look for diet, consumer and prey. Using reference books. Scan the contents page for these words and look them up in the index. Try looking up consumer and prey in the index to this book. Can you find out about the diet of an animal? Using the internet. Think carefully about the words you type into a search engine. Searches for crocodile diet and what do crocs eat will list different websites. Not all the information the internet is correct, so look carefully at the websites that come up on your search. Some are more likely to be correct than others. Animal wildlife. Crocodile facts. News fun. www cars. Click here to win. Croc eats. Whole cow. Quiz. Mai has found two websites with information about what crocodiles eat. Which think is more reliable? Do you? To find reliable websites, look for those that come from large organizations and are written by experts. Unreliable websites often have adverts and do not look as good.